Welcome back everyone. In this lecture I will actually prove the Schur's lemma, and then we will also see some consequences of Schur's lemma, so which will be used later in the theory of semi-simple algebras. So this is again like in any category of representations one can define Schur's lemma. Okay, so here if you have seen this in group theory representation theory of groups, okay, it's almost similar to that. Okay, so we start with again Lie algebra, and let's take two different representations. Okay, let's say V and W. So both of them are representations of G. So we will take it to be irreducible representations of G. So then if we have a map, let's say G module map phi from V to W, we want to understand what are all the possibilities for this map. Okay. So say this phi is a map from V to W which is actually a G module map or homomorphism. So what we have seen in the last class, if we take the kernel of this map, okay, and image of this map. So both of them are modules in the respective modules. Okay, this is a module inside V and this is module inside W. So both of them are G submodules. So suppose if we know that V is not isomorphic to W, so then what will happen? So you can see that this kernel phi, okay, so that that should not be 0. So what are all the options for kernel phi? Okay, let's not worry about this case. Okay, let's see, like kernel phi being a submodule of V. So what are all the options for kernel phi? So the kernel phi either has to be 0 or full, as V is irreducible. Okay. So now if you take this image phi, which is a module inside W, so that will imply this image phi either again 0 or full, again as W being irreducible. Okay. So now you can see that if V is not isomorphic to W, then what will happen? So the image of phi is actually cannot be W. If image of phi is actually W, then what will happen? The kernel is actually has to be 0. Otherwise, okay, so if image phi is W, so then kernel cannot be actually entire V. If kernel is entire V, then that would imply that image phi is 0. So that will imply that W is 0. So maybe we can start with V and W non-trivial. Okay. So non-trivial means non-zero irreducible representation. So assume dimension V and dimension W, they are all positive. I guess that was the inbuilt definition of irreducible representation. To begin with, irreducible representation should be non-zero space. So that means dimension of V and dimension W must be at least 1. So with that we can see that if image of phi is W, then the kernel phi cannot be entire V, that will force kernel phi is 0. So that means this phi must be an isomorphism. But that is not the case. We have started with V is not being isomorphic to W. Okay. So, that is actually says that image phi cannot be W. Okay. So, this argument immediately says image phi cannot be W. So, that forces image phi is being 0. So, that forces kernel is being entire space phi. Okay. So, that means phi must be trivial map. That means phi of V is 0 for all V in V. So, what will happen if V is isomorphic to W? Okay. We just saw that in that case we can have such maps. For example, if V is isomorphic to W, so you can take W to be V itself, not a problem. So, then for example, identity is one such G module map, and any scalar times identity, that is also isomorphism from V to V. Okay. So, now the question is there anything else? So, if you think about it, there are none other than that. Okay. So, again from the same argument we can see that kernel phi again either 0 or V, and image phi is either 0 or W. If image is full, okay, so if image of phi is full, so then kernel of phi, so that cannot be 0. So, that is also that cannot be full. So, that has to be 0. So, that makes this is actually isomorphism. So, we can replace. Okay. So, we can look at this modified question now. So, where phi is from V to V. Okay. So, I am replacing W by V because we know that V and W are isomorphic. So, consider this situation when phi is defined from V to V. So, then what happens since we are working over complex numbers, so phi must have an eigenvalue. Okay, of course, I am not mentioning we are all working over finite dimensional irreducible representations. Okay. So, everything is finite dimensional, that was declared in the beginning. So, that is why I am not mentioning it here. So, since V is finite dimensional, this map phi which is a linear operator on V must have eigenvalue. So, say lambda. Okay. So, then you can look at this phi minus lambda identity. So, which is a map from V to V. So, phi is G module map implies phi minus lambda identity V is also a G module map. So, that is not hard to verify, but if you look at the kernel of this phi minus lambda IV, so that must be non-zero, because lambda being eigenvalue, there exists a eigenvector associated with that. So, there exists V in V such that phi of V equal to lambda V. Okay. So, that means this non-zero vector V is inside this kernel of phi minus lambda identity V. But the kernel is being non-zero would imply that the kernel of this phi minus lambda identity V, which is being a submodule of V, it has to be exactly equal to V. So, that forces that phi minus lambda identity V is 0 on capital V. So, that forces that phi must be lambda times identity V. Okay. So, these two actually kind of analysis put together is called Schur's lemma. So, sometimes the statement 2 is also called Schur's lemma, but I would like to call both of them as Schur's lemma. So, what is Schur's lemma? So, let me state it. Schur's lemma, the very first statement, if V is not isomorphic to W, so again V and everything is as before, G is Lie algebra and V and W are finite dimensional irreducible G modules. So, these are all given data. If V is not isomorphic to W, then any map phi from V to W must be trivial map. Okay. So, that is what we proved. Okay. Yeah, if V is not isomorphic to W, then the image phi cannot be W, and so that means image phi must be 0. So, that means phi is trivial map. The second statement, if phi is from V to V, G module isomorphism, then phi has to be lambda times identity V for some lambda coming from complex numbers. Okay. So, these two are two important statements about irreducible representation and the maps between them. So, if you write it in terms of home, so we can actually denote this home space of G V comma W. So, that is it is a subspace of home V comma W, which is defined to be the set of all G module maps from V to W. So, it is not hard to see, this is actually a subspace. So, this is a subspace of home V comma W. So, which is all linear maps from V to W. Okay. So, in terms of this home G V W, Schur's lemma can be read as follows. So, home V comma W is trivial if V is not isomorphic to W, or otherwise it is just scalar times identity if V equal to W. Okay. So, now what is the corollary of this result, immediate corollary? So, you take again G to be Lie algebra over C and let V be an irreducible module. Okay, G module. So, if there is an element in the center of G, so which is those x in G such that x commutes with y for all y in G. So, then this Z must act as a scalar on capital. Okay. So, what is the meaning of that? There exists lambda in C such that Z dot V is given by lambda V for all V in V. Okay. So, this is actually an immediate consequence of what we have seen earlier, because what is the proof? The proof is, suppose Z is in the center. So, then what happens if you look at this action of Z on this capital V? So, then you can easily see that this Z actually commutes with the action of x. Okay. So, if you compute Z acting on x V for some x in G, so then this will be exactly equal to x dot Z dot V plus the bracket Z x dot V. Okay. So, for any x in G and V in V, we have z x dot V is given by x dot z dot V plus z x. Okay. So, that means z dot x dot V is given by x dot z dot V. So, this z x is 0. So, that would imply z x dot V is also 0. So, that proves z of x v is nothing but x of z v. So, that proves z defines G module map on capital. Okay. But V is given to be irreducible representation. So, from the Schur's lemma, we can see that Z on V is nothing but given by lambda times identity on V. So, this is actually allows us to define what is called this central characters. Okay. So, if you start with the Lie algebra and V is irreducible G representation. So, then one can define what is called this chi from the center of G to complex numbers given by chi of z equal to lambda z, where think this lambda z coming from this map z. So, where z acting on V is given by lambda z I V. Okay. So, where you think, so z acts on capital V as scalar multiple lambda V times lambda z times identity. Okay. So, now it is not hard to see that this is actually gives a linear map. Okay. So, that is I will leave it to you to check. So, z of G is actually abelian Lie algebra. So, z of G is abelian Lie algebra. Okay. So, this map chi one can easily check that it is a linear map. So, let me check. So, if you take chi of z1 plus z2, so this is given by lambda z1 plus z2. So, if you think about it, z1 acts or z1 v is given by lambda z1 times v. Similarly, z2 v is given by lambda z2 v. So, if you take z1 plus z2 and then act it on v, so you get lambda z1 plus lambda z2 acting on v. So, this is for true any v in v. So, that would imply that lambda z1 plus z2 must be equal to lambda z1 plus lambda z2. Similarly, if you take a scalar, so then you get scalar here, okay, and then that will also tell you that you get scalar outside C times lambda z2 times v. Okay. So, lambda C z2 will be equal to lambda times C times lambda z2. So, this forces that this is linear. Okay. So, this implies chi of z1 plus C times z2 is same as chi of z1 plus C times chi of z2. So, that implies chi is linear. But since z of G is actually abelian Lie algebra, so one can think this chi as representation of z of G. So, chi is indeed okay. So, since chi is linear map from center of G to complex numbers, one can think chi as Z of G representation. So, this is what called central characters. Okay. So, we have started with, so let me actually use V everywhere. Okay. This is chi V, because chi V is depending upon this capital V. Okay. So, what we have done, we have actually started with some G module, and then we have come up with representation of center of G. So, you start with finite dimensional irreducible G representations. So, from here you are actually defining one dimensional representation of center of G. So, the way we do it, you start with V and then you map it to chi V. So, sometimes it is important to actually understand. So, what happens to this central characters. So, these are all called central characters, and we actually have a very vast theory about central characters of semi-simple algebras. So, which we will actually see later. Okay. So, now I would like to end with one important remark about Heisenberg algebra. Okay. And then we will actually later move on to the representation theory of SL2C in the next lecture. So, there are like many interesting questions one can ask once we have introduced this representation theory. Okay. So, let me actually do one small problem here. So, that actually tells you that how interesting is the representation theory. So, recall the Heisenberg algebra, so which is spanned by x, y, z, okay, where x, y the bracket is given to be z and z is in the center of this H3. Okay. So, now one can easily show that. So, this is indeed solvable Lie algebra. Okay. The H3 is solvable. So, now using Lee's theorem, you can prove that any one dimensional representation of any irreducible representation of H3 must be one dimensional. So, let us say phi is actually representation of H3. Okay. So, V is irreducible H3 representation, let us say. So, now using Lee's theorem, what we have, there exists vector non-zero vector inside capital V such that, so this is going to be simultaneous eigenvector. So, that means given x dot V will be lambda of x V for all x dash, let us put x dash inside H3. So, that means this space generated by C V inside this capital V, this will become sub representation of V. But since V is irreducible, that will imply that C V equal to capital. Okay. So, this H3 because it is solvable, so all the irreducible representation of H3 must be one dimensional, and this is true for any finite dimensional solvable Lie algebra. So, that is immediate consequence of Lee's theorem. So, now what we will prove that, so this H3 does not have a faithful finite dimensional irreducible representation. Okay. So, let us say phi is a faithful representation of H3. So, that means phi is faithful. Actually, let us see what happens if we start with any representation. Okay. So, if phi is just a representation of this H3, so then what happens, you can look at this commutator formula. So, this x y is given to be z and z is inside the center of H 3. Okay. So, that is the commutating formula. So, now what is happening? So, if you take this x and y, so look at the action of this action on capital V. Okay. So, V will be invariant under both these actions. So, in particularly if I compute the trace of this x y as an operator on capital V. So, this is going to be 0 because the bracket x y on capital V will act as follows. So, this will act as okay. So, let me write it properly. The bracket x y acts on capital V as x dot y dot V minus y dot x dot V for all V in V, okay, because the bracket x y dot V is equal to this. So, that means this is actually a commutator, okay, inside inside that GL of V. Okay. So, basically what I am trying to say, if you take this phi of bracket x y, it is going to be bracket of phi x phi y. So, that means if you take the trace of phi x phi y, that is going to be 0, but on the other hand the trace of phi x phi y is nothing but phi of z trace. Okay. But what we have seen from Schur's lemma, this z is being in the center. So, this z is being in the center, that implies phi of z must be some scalar times identity on V. So, that means this trace of phi z should be lambda times dimension of V, and this put together implies lambda dimension V should be equal to 0. So, that will imply lambda must be 0. That means this phi of z is always 0. Okay. That means z acts trivially on any representation of H 3. Okay. So, this kind of interesting consequences can be derived from just by looking at the commutator of the Lie algebra. Okay. So, this is what we will do next time, and then try to understand the SL2 representation theory. Okay. So, just as a warm up, I gave this as a consequence of the Schur's lemma. So, I will stop here. In the next class we will start with the SL2 representation theory. Thanks.